Hi there, Physics Boss Man coming back at you. A lady pulls a mass of 35 kilograms on a sled a distance of 10 meters through the snow as shown. If mu, the coefficient of friction, equals 0.20, how much work does the lady do? With God's help, you can do physics. Boss, as you are created.
You are created in God's image.
To be fruitful and multiply.
Fill the earth and subdue.
Do it. Okay, since we already have a pretty good picture in the problem statement, the picture that we're going to draw as we interpret it is a free body diagram. So to draw the free body diagram, the goal is to represent all the forces. So we have the force of gravity is negative mg, it's in the downward direction. We have the normal force in the upward direction. We have the applied force, and this is the force that's applied at the 30-degree angle that the lady's pulling with. And we're not sure what the magnitude of that force is. And we have the frictional force, which is opposing the motion. So it's negative mu times the normal force. Now we need to use a little care here because some of the things that we're accustomed to being true in simpler situations aren't true in this case. For example, the normal force isn't simply isn't simply mg, because we know that the acceleration equals 0. So both the x and y components of velocity are constant. So the net force in the y direction is going to be 0, and this applied force is pulling up a little bit, so it's going to have the effect of reducing the normal force. Alright, so the principle that we're going to apply here, and actually there's several of them, which is one of the things that makes this a more interesting problem. The definition of work is the big idea that we're starting with. In other words, work is, and depending on the physics course that you're in, sometimes it's the line integral of f dot dr. If you're in a course without calculus, in that case the work might be the vector f dot product with the displacement vector. And so there's different ways that the definition of work is expressed depending on the physics course that you're in, but that's where we start. Newton's second law is also important here, and the definition of coefficient of friction. So all these ideas are in play. So to develop the solution, we want a bullet point plan, and so there's a lot of moving parts in this one. So let's go ahead and let's express.
God has crowned you with glory and honor.
Honor to rule over his creation. The forces as components. And in this case, if we go ahead and make our traditional coordinate system where x is horizontal and y is vertical, that's a convenient choice of coordinate system because the only force that's got more than one non-zero component is the applied force that the lady is exerting as she's pulling the sled at a little bit of an upward angle. So then we can identify all the horizontal forces. And this is convenient because this allows us to set the sum of all the horizontal forces equal to 0. And why is that true? It is true because the acceleration is 0, right? In that bit in the problem statement when it said that the lady was pulling the sled at constant velocity, there's no horizontal acceleration, which means the net horizontal force is 0. That's why it's true. Well, why is it useful? Well, we'll see that in the course of solving the problem, but if you think about it this way, at this point there's two unknowns in the problem that we think we're probably going to need en route to computing the work, right? We need the applied force and we need the normal force. So if the applied force is unknown, the magnitude of it's unknown, and the normal force is unknown, that's two unknowns. And it's convenient that by setting the sum of the horizontal forces equal to 0 and setting the sum of the vertical forces equal to 0, that's two equations. We have two equations and two unknowns. We have some confidence that we're going to be able to solve it. So the next step is to identify all the vertical forces. And once we've done that, then we can set the sum of the y components of the forces equal to 0. And the reason that this is true is because there's no there's no vertical acceleration. Alright, so this is going to give us two equations and two unknowns, so then we solve for the normal force and the applied force. We know what their directions are, so we're really just finding the unknown magnitude, right? The normal force is up, and the applied force is at that 30-degree angle in the picture. So once we get to this point, then the work is going to be the applied force dotted with the displacement. Another way you can think about this with the dot product is just going to be the magnitude of the applied force times the distance times the cosine of that 30-degree angle. Alright, so now we can begin to evaluate.
Science is a gift from God,
To help us master nature,
but sin added thorns and thistles.
requiring the sweat of your brow to succeed. So to begin the evaluation process, the x component of the applied force is just Fa cos theta. The y component is just Fa sine theta. So now, summing up the horizontal forces and setting that equal to 0, well, let's make sure, let's think about the other horizontal forces. Just be a little careful here before we go slinging equations. The force of friction equals minus mu times the normal force, the horizontal force in the negative x direction. And then we've got this one here. So summing those two together, we have minus mu times the normal force plus Fa cos theta equal to 0. And this is not just true, it's useful because this relates, the only two unknowns in this equation are the normal force and the applied force. So we can simplify all this. Solving for the applied force is going to be mu times the normal force over cosine of theta. Alright, so now let's keep track of our vertical forces. So we have the normal force, we have the gravitational force, and we have the y component of the applied force. So now if we add all these up, the sum needs to be 0. Alright, so now this is one equation, but there's two unknowns, the normal force and the applied force. Well, we've already solved for the applied force in terms of the normal force, so we can use that to simplify it. The normal force minus mg. Now I'm just substituting in the mu times the normal force over cos theta as the applied force, and then the sine theta, I'm just carrying it down. And before we drown in the alphabet soup here, let's just notice we've got one equation and one unknown. I mean, we're carrying around a lot of symbols, mg, theta, mu, but all those are known quantities. So now we can simply solve for the normal force. So it's convenient to put mg on the other side. It's also convenient to note that the sine theta divided by the cosine theta is tan theta. Now it's convenient to factor out the normal force. Now it's convenient to divide both sides by the term in parentheses.
Learning physics
Often requires prayer
as we submit
to Jesus Christ
as risen
King of Kings and Lord of Lords. Okay, so all this alphabet soup, we can just substitute in numbers that we know now, right? The mass was 35 kilograms. The acceleration of gravity is 9.8 meters per second squared. And then this factor in the denominator note is unitless, so that when we do all this, we come out that the normal force is 307.5 newtons. Now, let's just think about the units here for a moment. The denominator is unitless because mu is unitless and the tangent of an angle is unitless. So the normal force have units of mg, units of mass, kilograms, times units of acceleration, meters per second squared. And that's how we get it simplified to units of newtons. Now, so the last step is to go ahead and plug the normal force back into this expression for the applied force. And that's just plugging in the 307.5 newtons times the 0.2 divided by the cosine of 30 degrees. And so you do all that math, and that works out to be 71 newtons. All right. So now we have everything we need to compute the work. So the work is the applied force times the distance times the cosine of the angle. So that works out to be the 71 newtons times the 10 meters times the cosine of 30 degrees. And so that works out to be 615 units of newtons times units of meters or newton meters. And we also know that a newton meter is a joule. So the work done by the lady is 615 joules. So let's go ahead and assess.
We reign by surrender.
We reign by surrendering to Jesus and praying for our daily bread, which includes success
in our schoolwork.
God will answer and lighten our yoke and the impact of the thorns and thistles in our labor. Units. We were careful with our units along the way. We did the math on the units at every step. We were expecting units of joules because work has units of energy, and we got units of joules. What about the sine? Yeah, pulling something through the snow is going to be positive work to overcome the work of friction. What about the magnitude? And this is going to require a little more thought. Well, how can we easily estimate not the exact magnitude, but something in the ballpark of the magnitude of pulling a sled through the snow? Well, let's ask this question. How much work would it take, and it's a much simpler physics problem, if you simply pulled the sled along with a force parallel to the horizontal, with a horizontal force, right? If you're pulling with a horizontal force rather than pulling at that upward angle. Well, that makes everything easy. In that case, the work is just the force times the distance. And the force, you're just balancing the frictional force. So the applied force is just mg mu to pull it through the snow, and then times the distance d. So you plug those numbers in and you get 686 joules. So exerting a little bit of an upward force, pulling something through the snow, because you're reducing the normal force. So you're reducing the friction by reducing the normal force. So the work that you're doing is a little less than it would be had you simply applied the horizontal force. So that assessment tells us that our magnitude is about right.
Written in the Word, in the good, good Word, is a message from our God. Gonna tell you all about how to get to the kingdom, the good life. Written in the Word, in the good, good Word, is a message from our God. Gonna tell you all about how to get to the kingdom, the good life. Oh, I love Jesus.